Hello everyone. What we'd like to do in this video is take a look at the graphs of the other four trig functions that we haven't seen yet. We've seen the graph of sine, we've seen the graph of cosine. What's the graph of tangent look like? What's the graph of cotangent look like? What does cosecant look like, and what does secant look like? Okay, let's do it. Let's go ahead and start with tangent. Out of the four we're going to graph, tangent is my favorite. Tangent's the most intuitive to me. Okay, we'll start with tangent. Okay. The way I like to think about the graph of tangent, I'll give you two different ways to think about it. The first way I'm going to show you to think about it is usually not the way that I remember the graph of tangent, but it'll help us when we're trying to figure out the graph of cotangent. So the best way to think about tangent of x, or how about tangent of theta if you like, tangent of x. Well, tangent is the same thing as if we think about SOHCAHTOA. Some old hippie caught another hippie tripping on acid. We're talking about tangent, so we're tripping on acid. So tangent is opposite over adjacent. So what is tangent? Tangent is opposite over adjacent. So I know I'm saying x here. How about I put a theta instead? Tangent of theta is the same thing as sine of theta over cosine of theta, opposite over adjacent. So let's recall a nice tool. If you've taken Math 141 recently, this is like a rational function. I have a numerator and a denominator. So what I'm going to think about is where the x and y intercepts are of the graph and where the vertical asymptotes are going to be. So when you're looking at a rational function, if I want to know what values of theta should I plug in to get an output of 0, well, a fraction is only 0 if its numerator is 0. So tangent of theta will be equal to 0, well, when sine of theta is equal to 0. So if I think about the ratio, when I have a numerator of 0, tangent will be 0. So tan of theta will be 0 when sine of theta is 0. We'll also have that tan of theta is undefined. When cosine of theta is equal to 0. Notice that we can't divide by 0. That's like the biggest rule in math. Thou shalt not divide by 0. So, when the denominator is 0 and cosine is 0, that's when my graph is undefined. Normally these features, if we're looking at a graph, normally if I have a location where the denominator is 0, in a graph that usually displays an asymptote. So for this situation, we will have x-intercepts. We'll have x-intercepts of tangent. For this situation, where the denominator is 0, where my function is undefined, tangent will have vertical asymptotes. Vertical asymptotes. Okay. So let's keep this in mind. I'm going to erase a little bit of what we have here. Okay. Okay, so let's give it a sketch. What does the graph of tangent look like? Okay. Let's first mark the x-intercepts of the graph. Okay, the x-intercepts are going to happen when sine of theta is 0, when I have 0 over a non-zero number. So my x-intercepts will happen when sine of theta is equal to 0. Well, when is sine of theta equal to 0? Let's record a few spots here. What is this? Is the coordinate. X is 1, y is 0. Let's see, x is 0, y is 1. X is negative 1, y is 0. X is 0, and y is negative 1. Well, it looks like that sine is 0. When's the y-coordinate 0? Well, at 0. So if I'm graphing tangent of theta, and here's theta, it'll have an x-intercept at 0. Okay, it'll have another x-intercept at pi. So here we'll have pi. Okay, then it'll have another x-intercept at 2 pi. So when theta is 0, pi, 2 pi, 3 pi, 4 pi, 5 pi, any multiple of pi, tangent will have an x-intercept. Okay. Even if I go backwards, even if I'm over here at negative pi, I'll still have an x-intercept. Now where am I going to get vertical asymptotes? I'm going to get a vertical asymptote on locations where tangent is undefined. That's when cosine of theta is equal to 0. I want to know when I'm dividing by 0. Well, it looks like cosine is 0 when my angle is pi over 2. So here's pi over 2. Tangent is undefined here. I'll have an asymptote. Here, I'll also have one where? At 3 pi over 2. So I'll have another vertical asymptote. Okay, and I'll also have one at negative pi over 2. If I go backwards, pi over 2, negative pi over 2, cosine 0 here also, I will have another, let's make the scaling a little bit better. I'll have another vertical asymptote at negative pi over 2. And I'll have our x-intercept at negative pi. Okay. So notice that for tangent, what is always going to happen is it's going to alternate between x-intercept, asymptote, x-intercept, asymptote, x-intercept, asymptote, x-intercept, asymptote, x-intercept. So I know that tangent is, the graph has to be approaching these asymptotes. But I want to know, does the graph approach the asymptote going up or does it approach it going down? This is where we want to think about whether sine is positive or negative in each of these 4 quadrants. Well, in quadrant 1, sine is positive and cosine is positive. So, I don't know, maybe I'll write it in blue. Tangent of theta is positive in quadrant 1. Okay, over here, cosine or the x-coordinate is negative and the y-coordinate is positive. Here, tangent of theta is negative. Here, since both sine and cosine are negative, take 2 negatives and divide them, you get a positive. Tan of theta is positive here. And tan of theta, let's see, sine, the x-coordinate is positive, the y-coordinate is negative. Tangent will be negative in this quadrant. Okay, so let's see what's going to be happening. Well, in quadrant 1 is between 0 and pi over 2. Well, tan is positive there, so I always have to be above the x-axis in this first window. So the graph of tangent has to be doing this. Similarly, here we would be in the second quadrant. Well, tangent is negative there, so the graph has to be completely below the x-axis here, and it has to be approaching this asymptote, so the graph would have to do this. Okay. Between pi and 3 pi over 2, that's the third quadrant, tangent is positive. So we'll get this. And similarly, if I'm in this would be the fourth quadrant, tangent is negative. So we're going to have something that looks like this. And the graph is going to repeat itself. It's going to repeat itself. So on and so forth. So what does tangent look like? How do I remember what tangent looks like? I don't know, to me, tangent kind of looks like x cubed. It looks like an x cubed function, except it's repeating itself. That's how I remember tangent. At least the graph. But I don't know, didn't that seem like a lot of work? Didn't that seem like a lot of work, what I was doing here? Where are the x-intercepts? Where are the asymptotes? Okay, here's something better. What is tangent on the unit circle? Well, tangent is sine divided by cosine. Okay, so tangent is sine divided by cosine. Sine tells us a height or a rise. Cosine tells us a width or a run. So sine is a height over a width. Tangent is a height over a width, or tangent is a rise over a run, a vertical change over a horizontal change. That smells like slope. That smells like slope. Sine over cosine, rise over run. What is tangent? Tangent is the slope of that line. Tangent is the slope of this line as you rotate it around. Man, forget about this. I mean, don't really forget about it. I mean, you should understand what I just did. That'll help us with cotangent. But let's think about it a lot easier. Tangent is the slope of this line as we're rotating around the unit circle. So let's just graph it thinking about it that way. That's how I think about it. Okay. So, I don't know, here's 2 pi. Here's pi. Here's pi over 2. Here's 3 pi over 2. Okay, well, let's start at 0. Tan of theta. So what's going to happen? Well, if I'm at 0 degrees or 0 radians, the slope of this line is 0. Now as we rotate around, what's happening? The slope is getting bigger. The slope is getting bigger until you get to pi over 2. You have a vertical. You're going to get a vertical line. There's no slope there. The slope is undefined here. No one can climb this wall unless you're Spider-Man. So what's going to happen is the slope is going to be getting bigger. The slope of that line gets bigger and it approaches infinity. That's why there's an asymptote here. So now I have an undefined slope. The slope is infinite here. Then what happens? Move a little a little bit more over. Oh, a little bit more over. Oh, now you have a super negative slope. A super negative slope. Now what we're doing? More negative. I'm sorry. It's negative. It's really negative. And now it's getting less negative, less negative, less negative until you get to a slope of 0. Until we get to a slope of 0. Okay. Now I'm at a slope of 0. Whoa. And now what's going to happen is now I'm going to go a little bit further. Now I'm going a little bit further. Now the slope is positive. The slope is positive again. And it's getting more and more and more positive. More and more and more positive. Till we get to another infinite slope. I have another asymptote here. That's how I remember the graph of tangent. And it just repeats itself. It just repeats itself. And we have tangent. Beautiful. Beautiful. Okay. So this is the graph of tangent. Just remember tangent is the slope of that line. It's the slope of that line as we rotate around. Okay, here's tangent. Beautiful. Let's make a note about tangent. We should notice its period. What is the period of tangent? Well, it's going to be the shortest distance. It's going to be the smallest x value or the smallest window where the graph repeats itself. Well, we just need one of these. Okay, what's my window for one of these? Well, I'm going from negative pi over 2 to pi over 2. This is a length of pi. This is a length of pi. I have half a pi. I have another half a pi. I got a whole pi. I got a whole pi. Got a whole pi. The period. The period is pi. Now you could measure from here to here, but I guess if you also broke it off here, you could think of, this would still be one period. It still repeats itself. If you think about it, in this window, the period would still be pi. So we should pay attention to this. The period of tangent is pi. The period of sine and cosine is 2 pi. The period of tangent is pi. And you can see that just by thinking along the unit circle. Okay, look, the slope is 0. Then the slope is going to be positive till I get to an infinite slope. Okay, then what's going to happen? Then I'm going to get a negative slope. And I'm going to go all the way back. I'm going to go all the way back till I get a slope of 0 again. Well, once I'm here, then I'm back to a positive slope. I'm repeating myself. So tangent, if I'm thinking about the slope of the line, all the possible slopes will just really be between 0 and pi. The period of tangent is pi. Okay, there we have it. Okay, so that's what I remember. That's how I remember tangent. It's the slope of the line on the unit circle. Okay, another good thing to realize is that tangent also goes from x-intercept to asymptote. X-intercept, asymptote. X-intercept, asymptote. We should keep that in our mind, okay, because now we have to graph cotangent. Okay, so our next graph, let's do cotangent. Okay, and I guess let's just keep just a quick picture of the unit circle up. Okay, here's our unit circle. Okay, so let's graph cotangent. Now remember what cotangent is. Cotangent is the reciprocal of tangent. So if tangent was sine over cosine, well, then cotangent is cosine over sine. Okay, so cotangent is cosine over sine. So that's a good thing to remember. So tangent is cosine of x over sine of x. Okay, let's record these spots. What we have? 1, 0, 0, 1. Negative 1, 0. 0, negative 1. Okay. theta, cosine theta, sine theta, cosine theta, sine theta. Okay, so let's think here. So now what we should notice is I'm going to get x-intercepts, in this case now when cosine of x is equal to 0. If this x is throwing out, put a theta here. Put a theta here. Okay, I'm going to have x-intercepts when cosine of theta is equal to 0. And I'm going to get vertical asymptotes, I'll just write VA, vertical asymptotes when sine of theta is equal to 0. So let's just sketch those. Okay, so we're going to graph cotangent of theta, so here's theta. Okay, let's see here. Let's look for x-intercepts. X-intercepts happen when cosine of theta is equal to 0. Well, the x-coordinate is 0 at pi over 2. At pi over 2, I'll have an x-intercept. And at, what, 3 pi over 2. So here's 3 pi over 2. I have x-intercepts. Okay, where am I going to have vertical asymptotes? That's when sine is 0. Sine is 0. The y-coordinate is 0 at 0. I have a vertical asymptote at 0. At 0, and I have another vertical asymptote. At pi. And I'll have another one over here at 2 pi. So notice in this case, now it goes asymptote x-intercept, asymptote x-intercept, asymptote x-intercept. For tangent, they were flip-flopped because these were flip-flopped. For tangent, it went x-intercept, asymptote, x-intercept, asymptote. So for the difference between tan and cotangent, a lot of it has to do with their x-intercepts and their asymptotes swap places. Okay, so now what I'm going to do here is, now I have really my quadrants of my unit circle. First quadrant, second quadrant, third quadrant, fourth quadrant. So now let's just see what's going on here. Well, since tangent and cotangent are just reciprocals from one another, tangent and cotangent have the same sign in all the quadrants. So since tangent was positive here, cotangent is also positive here. Okay? Since tangent was negative here, cotangent of theta is also negative here. Since tangent was positive here, cotangent is positive here. Since tangent was negative here, cotangent of theta is negative in quadrant 4. So let's just piece it together. Okay, in quadrant 1 between 0 and pi over 2, cotangent is positive, so I'm always above the x-axis. So cotangent has to look like this. Okay, in the second quadrant, cotangent is negative. In the third quadrant, cotangent is positive. And in the fourth quadrant, cotangent is negative. So here we have it. Here's the graph of cotangent. We can go backwards if you like. So let's see what negative pi over 2 and negative pi, x-intercept, asymptote. So cotangent, it's like this. Okay. I remember the graph of tangent much better than I remember the graph of cotangent. I remember the graph of tangent, and I just remember that I'm reciprocating it, so my x-intercepts and my asymptotes are going to flip places, and I just remember whether cotangent is positive or negative in those regions, whether cotangent is positive or negative in each of the 4 quadrants, and then I piece the graph together there. But here is the graph of cotangent. I promise you that when I'm graphing cotangent, I pretty much do this exact exercise every single time. When I'm graphing sine, cosine, and tangent, I can throw those together here pretty quickly because I know, an easy way to think about what they are on the unit circle. Cotangent, cosecant, and secant, they do have meaning on the unit circle, but it's not as obvious, and I just usually forget about it. I just remember sine, cosine, and tangent, and then I can piece together the other 3 from there. So here's the graph of cotangent. Okay, we were doing cotangent. That's what we did. We just did cotangent. Beautiful. Okay, let's take a look at the graphs of cosecant and secant. Now the way I remember the graphs of cosecant and secant is I usually think about first the graphs of sine and cosine, and I think about reciprocating those outputs. I'll show you what I mean. So let's first do cosecant. So for cosecant, we should remember that the definition of cosecant is, or at least how I remember the definition of cosecant, is it's the reciprocal of sine. It's the reciprocal of sine. So what I'm first going to do is I'm going to first graph sine of x, and then I'm going to think about reciprocating the output. So let's graph sine first. Okay, here's 0. Here's 2 pi. Pi. Pi over 2. 3 pi over 2. And sure, negative 2 pi, negative pi, negative pi over 2, and negative 3 pi over 2. Sine has a amplitude of 1. Okay, sine starts at equilibrium. So we'll go here, 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 here. So here's the graph of sine. Looks like I drew 2 periods. Okay, so now when I'm thinking about the graph of cosecant, well, cosecant is 1 over sine, so I need to reciprocate all these values. So since I'm dividing by sine of x, I want to think about the locations where cosecant is undefined. Cosecant is undefined whenever sine of x is 0. So if you're looking at all the x-intercepts of sine, the x-intercepts of sine will turn into the vertical asymptotes of cosecant. So cosecant is going to have a vertical asymptote at 0, at pi, and at pi over 2, and also at negative pi and negative pi over 2. Okay, so now what I'm going to do is I'm going to think about all of these outputs, and I'm going to think about reciprocating them. Okay, the first thing to think about is, first of all, let's think about the value of cosecant at pi over 2. Well, if you plug in pi over 2 into sine, the output is 1. If I want to know what cosecant of pi over 2 is, it's 1 divided by 1. So cosecant and sine will agree here. They'll also agree here, here, and here, because 1 over 1 is 1, 1 over negative 1 is still negative 1, so on and so forth. Okay, now what's going to happen when I go outside of here? Well, you could think that the graph has to approach these asymptotes. So you might think that it has to do this. You would be right. But let's think about why. Well, notice when I'm in this region between 0 and pi over 2, all my outputs are between 0 and 1. What happens when you do 1 over a number between 0 and 1? What happens when you do 1 over a fraction? Those should be getting bigger. For example, what is 1 over a half? You could think to yourself, I don't know, how many times does a half go into a whole? I hope you believe 2 times. Or you could think about reciprocating and multiplying. So 1 over a half is 2. What if it's like a tenth? What if it's 10? 1 over a tenth. Well, how many times does a tenth go into a 1? I hope you believe 10 times, or just reciprocate and multiply. Okay, so when I'm plugging in numbers that are closer to 0, 1 over a number getting closer to 0 is getting larger. So cosecant must be doing this. And similarly, it'll be doing this over here. So the cosecant graph will be approaching these asymptotes. And there we have it, the graph of cosecant. How do I graph cosecant? I graph sine every single time, and I think about reciprocating these outputs. So here, what we have in black is the graph of cosecant. So what cosecant does is it kind of has these little parabolas, and they alternate. And so on and so forth. Okay, so I guess another thing to notice is the period. I think I forgot to say it, but I guess I forgot to mention it for when we did cotangent. The period for cotangent should also be pi. The period of tangent is pi. The period of cotangent should also be pi. For the period of cosecant, well, notice I get my upper and my lower parabola between 0 and 2 pi, and those will repeat itself. So I hope you can see the period will be 2 pi, which isn't surprising because the period of sine is 2 pi, so since cosecant is 1 over sine, they should have the same period. Okay, let's do secant. Let's do secant. Okay, secant, the last one. What I would like you to do is I'd like you to pause the video and try to get sketch a graph of secant on your own. The key thing that you should remember, the key thing that I remember, is secant is defined as 1 over cosine of x. Give it a shot. Okay, let's do it. So let's graph cosine first. Okay, cosine. Cosine starts at the amplitude, at the upper part of the amplitude. So cosine starts at 1, then it'll alternate. Okay, so cosine, because I'm drawing 2 periods of cosine, looks like this. Okay. Secant is undefined when cosine of x is 0. So all the x-intercepts of cosine will turn into the vertical asymptotes of secant. So I'll have a vertical asymptote here, a vertical asymptote here, a vertical asymptote here, and a vertical asymptote here. Okay. And now, if I'm doing 1 over 1, 1 over 1 is 1. And 1 over a fraction, 1 over a number between 0 and 1 is something bigger than 1. So, secant should be doing this. That's how I remember it. So on and so forth. So you can see that really secant and cosecant are really just shifts of one another. That's not surprising because when you look at the graphs of sine and cosine, they are also kind of just shifts of one another. Okay, let's think about the period. I hope we can see the period will also be 2 pi. You could think from here to here. Let's see, what do I have? I have this distance is, that's where I have an upper and lower parabola, happy face, frowny face parabola. This distance here is pi over 2 plus 3 pi over 2, 4 pi over 2. That's 2 pi. You could think that this distance is 2 pi. Or if you think about here, if you think about from here to here, from 0 to 2 pi, it's going to keep repeating itself if I take this picture and keep repeating it. Here I got half of the smiley face, and here I'd be connecting the other part of the smiley face. So the period for secant will also be 2 pi. So as a recap for remembering the periods of all 6 trig functions, there's only 2 that are different. The periods of sine, cosine, secant, cosecant will all be 2 pi. The only one that's different is tangent and cotangent. The period of tangent and cotangent will be pi. Okay. So what we're going to do in the next video we'll take these graphs here and we'll think about transformations of them. We'll see you then. Take care.